Welcome everyone. Myself Carl Joseph Samuel from the Department of Biotechnology, Kamaraj College of Engineering and Technology. In this video, we are going to discuss about metabolic stoichiometry. What we are going to focus on this video is how to calculate stoichiometric coefficients, degrees of reductions, respiratory quotient and yield coefficients for a given biochemical reactions. Before going into the video, we need to know what are stoichiometric coefficients. Stoichiometric coefficients are added to or coefficients in a chemical reaction to balance the input and output of a given reaction. For example, we all know the reaction formation of water from the hydrogen and oxygen. So H2 plus O2 gives H2O. So if you see this reaction here, there are two atoms of hydrogen and in the product also there are two atoms of hydrogen. So it is balanced. If we see the number of oxygen atoms here, two atoms of oxygen is going into the reaction, but at the end of the reaction there is one atom of oxygen is present in the one molecule of oxygen. So this is not balanced. So to balance this, what we can do is we can add, so here are two oxygen atoms and we can add to equate it, we can add two molecules of water molecule. There are two oxygen atoms. So we can put a 2 here. Now there are 4 atoms of hydrogen. So to balance that, we can put 2 here. So the 2 here and the 2 here are called as stoichiometric coefficients. Why it is important in a biochemical reaction is when we are giving in a fermentation reaction, when we are giving the substrate and how much product is formed, it is important to know how much efficient the process is. To find out that stoichiometric coefficients are important to calculate the yields of the reaction. Next important parameter is yield coefficient. Yield coefficients are used to tell how much yield is obtained from a particular substrate or how much oxygen is required to use to produce a particular amount of biomass. So to do that, we can calculate the yield coefficients are denoted as Y in the subscript we have added Yx by S. So this is a yield coefficient for biomass with respect to the substrate consumed. Similarly, yield coefficient of oxygen is written as Yx by O2. So here the amount of biomass produced is divided by the amount of substrate consumed to give us the yield coefficient Yx by S, and the amount of substrate produced is divided by amount of oxygen consumed is used to give us the Yx by O2. Third important parameter is respiratory quotient. Respiratory quotient or RQ is defined as the how much moles of carbon dioxide is produced per mole of oxygen consumed. So respiratory quotient RQ is given as RQ is equal to moles of CO2 produced divided by moles of O2 consumed. Last important parameters is degrees of reduction. For degrees of reduction, the number of equivalent atoms available is divided by the number of carbon atoms present. So it will give the number of equivalent atoms available, equivalent electrons available per atom of carbon. These are the 4 important parameters that are required when calculating a stoichiometry of a biochemical reaction. So next we can calculate how a stoichiometric equation is calculated for a biochemical reaction. I have given a biochemical reaction here. So in this reaction, hexadecane is used as the substrate and the biomass is produced. So this is the biomass that is produced. This is experimentally determined. This organism is assumed to convert 2/3 of the given carbon into a biomass. So given here is 2/3 of converted biomass. So first, to calculate the stoichiometric coefficient, so first to calculate the stoichiometric coefficients, first we need to balance this equation. So balancing the equation, the coefficients that P, Q, R, S and T that is availed when balancing the equations are called as the stoichiometric coefficient. So to balance this equation, what we can do is we can take element by element. So here there are only 5 elements: carbon, hydrogen, oxygen, nitrogen. Here there are only 4 elements, so carbon, hydrogen, oxygen and nitrogen. So we can balance the electrons, balance the atoms, elements individually. So first we can write the carbon balance. So to carbon balance, first here there are 16 carbon atoms that is present in the substrate is converted to carbon atoms present in the biomass and carbon atoms present in the carbon dioxide. So we know that 2/3 of the carbon atoms initially present is converted to biomass. So what we can assume is 16 is converted into 16 carbon atoms that is present in the substrate is converted into 4.4 carbon atoms of the biomass. I am taking the coefficient R, and 1 carbon atom present in the carbon dioxide, I am taking the coefficient T. So this comes from the biomass and this comes from the CO2. We know that 2/3 of the carbon dioxide is converted to biomass. So this biomass will account to 2/3 of 16 and this carbon dioxide will account to 1/3 of 16. So to find out that, so we can write this equation in the manner R 4.4 R is equal to 2/3 of 16. So which will give us 10.667, and if we calculate the R from here, 10.667 divided by 4.4, which will equal to 2.242, which will be equivalent to 2.4242. Remaining 1/3 of the carbon that is present in the T, so T is equal to 1/3 into 16, which will account to 5.33. So these are the two, first we have calculated the 2 stoichiometric parameters. Next, so based upon these 2 stoichiometric parameters, we can calculate the next elements balance. So I am writing the equations, writing the stoichiometric balances available here. R is equal to 2.4242 and T is equal to 5.33. So next element, what is the next element we can concentrate on is, next we can concentrate on the nitrogen. So here 1 nitrogen atom is present in the with the coefficient with the stoichiometric coefficient of Q, and nitrogen atom 0.86 nitrogen atom is present in the biomass. So we can write that as, for nitrogen balance, one atom of nitrogen is present in the substrate, that is Q is equal to 0.86 R. So we know the value of R from the previous calculation. So what we can do is 0.86 into 2.4242. So Q is equal to, next Q will be 2.085. So this is the next balance we have written. Next we can write the hydrogen balance. So for hydrogen, next we can write the hydrogen balance. Here hydrogen is present given as the substrate and nitrogen. So we can write that as 16 is present in the substrate, and in the nitrogen we have 3Q. 3Q present in the nitrogen is equal to hydrogen in the substrate amounts to, hydrogen in the biomass amounts to 7.3 R plus 2 into S. So we know the values of Q and R. If we substitute this and if I simplify it, and we will get the value S is equal to, we can substitute the values of Q and R here. (16 plus 3 into 2.085 is equal to 7.3 into 2.4242 plus 2 into S. If we simplify this, we will get the value of S is equal to 11.2788. So we now have the values of R, T, Q and S. So we don't know the value of P. So next we can write the oxygen balance to find out the value of P. Next is O2 oxygen balance. So to find out the oxygen balance, we need to find out where are the oxygens are present. Here in the substrate, oxygen is given only as the molecular oxygen, and in the product we have biomass oxygen 1.2 and water oxygen 1 atom, and in carbon dioxide there are 2 atoms. So we can write that as 2P is equal to, in biomass we have 1.2 oxygen atoms, R into 1.2, and in the hydrogen we have water we have 1 atom, and in carbon dioxide we have 2 atoms. So in water we have 1 atom, and in carbon dioxide we have 2 atoms, 2T. So now if we simplify this, if we substitute the values of R and 2P is equal to, R value of R is equal to 2.4242 into 1.2 plus S, value of S is 11.2788 and plus 2 into the value of T is 5.33. If we sum all this and divided by 2, we will get the value P is equal to 12.4267. Once we find out all the stoichiometric coefficient, we can substitute that in the biomass biochemical equation and use it to find out the degree yield coefficients, degrees of reduction and respiratory coefficient. So next what we are going to do is we are going to find out the yield coefficient. Here we are going to find out 2 yield coefficients. So one is Y x by S and another one is Y x by O2. So this is biomass yield coefficient and this is oxygen yield coefficient. To find out the biomass yield coefficient, we need to find out Y x by S is equal to, here we have biomass for each molecule of substrate we have 2.42 grams of biomass. So moles of biomass. So what we are going to do is 2.4242 into molecular weight of biomass divided by, and moles of substrate, here molecular weight of substrate. If we calculate the molecular weight of biomass by substituting the atomic weight of carbon, hydrogen, nitrogen and oxygen, it will account to 91.34, and if the molecular weight of substrate is 226. So substituting that 2.4242 into 91.34 divided by 226 will give us the yield coefficient Y x by S is equal to 0.97, 0.9797. So similarly we can find out the yield coefficient Y x by O2 is equal to, here similarly the amount of biomass, molecular weight of biomass 2.4242 moles of biomass is present. So molecular weight of biomass divided by, here we have 12.4269 moles of oxygen, 12.4269 into molecular weight of oxygen is 32. If we substitute the molecular weight of biomass and oxygen, we will get the molecular weight of oxygen as 0.5 yield coefficient with respect to x by O2 is 0.558. So, these are the yield methods to calculate the yield coefficient. So, next what we can do is we can calculate the degrees of reduction for the biomass and the degrees of reduction for biomass and substrate. So, for biomass the molecular formula is C 4.4 H 7.3 N 0.86 and O 1.2. So, the degrees of reduction is defined as the number of valence electrons per gram of carbon atoms. So, number of valence electrons divided by number of carbon atoms. So, if we find out the number of valence electrons for this, so we have 4.4 carbon atoms, so for which the valency is 4, and here we have 7.3 hydrogen atoms, so for which the valency is 1, and here we have 0.86 nitrogen atoms for which the valency is -3, and we have 1.2 oxygen atoms for which the valency is -2. So, if we sum these and divided by, there are totally 4.4 carbon atoms is there. So, divided by 4.4 we will add. So, if we sum these and if we solve this, we will get the valency of 19.92 divided by 4.4. If we solve this equation and if we sum all these, we will get 19.92 and divided by 4.4 we will get 4.572 as the yield coefficient for degrees of reduction for biomass. Similarly, we can calculate the degrees of reduction for substrate also. So, for degrees of reduction for substrate, we have C16 H34. So, here we have 16 carbon atoms for which the valency is 4 and 34 hydrogen atoms for which the valency is 1, and divided by we have totally 16 carbon atoms. So, if we do that, we will get 98 divided by 16, which will amount to 6.175. So, these are the degrees of reduction. Next, we can calculate the respiratory coefficient. Next, we can find out the respiratory quotient RQ by finding out the number of moles of CO2 divided by number of moles of O2. So, if we go back and see what we have the equation here, we have 5.33 moles of CO2 for 12.4269 moles of oxygen. So, that is equal to 5.333 divided by 12.426. So, we will get the respiratory quotient of 0.4291 as your respiratory quotient. To summarize, we have 4 important components in metabolic stoichiometry. First one is stoichiometric coefficient, second one is yield coefficients for which we can calculate for substrate and oxygen, and also any other compounds for which the yield is produced. Third one is we have the degrees of reduction. So, degrees of reduction is calculated by the number of valence electrons that is present per gram of carbon atom, and finally we have the respiratory quotient. Respiratory quotient is calculated by the number of moles of carbon dioxide produced per molecule of oxygen consumed. So, these 4 are the important parameters that is required in a bioprocess engineering industries to calculate how much of the substrate we are giving and how much of the yield we are availing, how much energy is put into this process, and how efficient is the processes. Thank you everybody.